This is the last video session of the fourth module. In this session, we'll be discussing three main topics: what we mean by attribute preserving decomposition, dependency preserving decomposition, and lossless decomposition. We get a problem for university using this last one, lossless decomposition, usually. So it's an important problem. So let's try to understand these three terms one by one. So first one is attribute preserving decomposition. Now what do you mean by decomposition? Say there's a relation like R and you decompose it into two, three relations. Now when is there a need to decompose into multiple relations? Like we had seen in like when we used to do 2NF, when we used to convert such a relation into 2NF, we used to split the table into three different relations in order to satisfy 2NF. So in similar situations, we split the table into different relations, or we split the relation into different relations. That is, we decompose the relation into multiple relations. So when we decompose like this, we should ensure that no attribute is lost. So if no attribute is lost, we can say that that decomposition is an attribute preserving decomposition. Let's see an example. So and this was the original relation, which consists of A, B, C, D, E, F, G, and H. So when we decompose this into 3 to satisfy 2NF, all the attributes over here should appear in any one of the relation. So A, B, C appears over here, D appears over here, E appears over here, F appears in this, GH appears over here. So all the attributes are appearing in any one of the decomposed relation. So we can say this is an attribute preserving decomposition. So hope you got that term clear when we say a decomposition is attribute preserving. Next term we need to understand is dependency preserving decomposition. Say we had a relation R and a set of functional dependencies in R, x to y kind of dependencies in R. When we decompose the relation R into R1, R2 and so on, all the dependencies in R should be there in the decomposed relation as it is, or it should be inferred from the dependencies in the decomposed relation. So no dependency should be lost. So that is what we mean by dependency preserving property of a decomposition. Let's just read this definition. Relation schema R is decomposed into a set of relation schema D, where the decomposition consists of M relations if each functional dependency x to y specified in F either appear directly in one of the relation schema Ri in the decomposition D or could be inferred from the dependencies that appear in Ri. So all the dependencies that existed in R should be there directly in R1, R2 and Rm, or it should be inferred from the dependencies that exist in this decomposed relation. So if so, we can say it's a dependency preserving decomposition. Let's see an example of a decomposition that is not dependency preserving. So imagine, don't read this for the time being, just consider this example. Consider the relation R consists of SSN, ename, pnumber, pname, plocation and hours. And we suppose we decompose it into two relations, R1 and R2, where R1 consists of ename, plocation and R2 consists of SSN, pnumber, hours, pname and plocation. Suppose we decompose this relation into these two relations, and the dependencies that already existed are these three, that is SSN gives ename, pnumber gives pname and plocation, SSN pnumber gives hours. Ignore this part also for this example, just concentrate on this part. So we need to see whether all these three relations exist in when we decompose it this R into R1 and R2. Let's take the first one. SSN gives ename. So SSN gives ename. So in this relation we cannot have that dependency, SSN gives ename. In this Also, we cannot have SSN gives ename. Neither can we derive it from any of the existing dependencies also. So this dependency, that is SSN gives ename, is getting lost when we decompose in this manner. So such a decomposition, if we are opting for such a decomposition of this R, we say that this decomposition does not preserve the property of dependency. That is dependency, it is not a dependency preserving decomposition. So this was an example. Ignore this metrics for the time being, it's for the next topic. So this was an example where the dependency is not being preserved and when it is decomposed. So the next topic is non-additive or lossless join property of a decomposition. What we mean by lossless join property. Now suppose we decompose D, the one thing we need to ensure is when we take the natural join of the decomposition, that is if R is decomposed into R1, R2, R3, and we take the natural join of R1, R2 and R3, there should not be any spurious tuples generated. Hope you remember what spurious tuples are. We had discussed that term during the beginning of this module. Spurious tuples means those tuples that does not, or those rows that does not originally exist in the relation. If such spurious or non-existing rows are created on taking natural join, that is a bad thing. That should not occur. So if the natural join of the decomposition does not generate spurious tuple, we say it satisfies lossless join property. So that is this term. When do we say a decomposition is non-additive or lossless? It is when if we take the natural join of the decomposition and no spurious tuples are generated, we can say it preserves non-additive or lossless join property of the decomposition. Now, there should be a standard mechanism to check whether spurious tuples would be generated. Like if it consists of 1 lakh rows, we cannot manually keep on checking each row to see whether a spurious tuple is generated. So there should be a standard algorithm or standard mechanism to check whether spurious tuples are generated. Next we will be going to that. This is important and from a problem could be asked from this topic. So first understand what we mean by lossless join property or non-additive join property. It means if we take natural join of the decomposition, that is R is decomposed into R1, R2, Rm, and if we take the natural join of this decomposition, there should not be any spurious tuples generated. We should be getting the original relation back. All the rows in the original relation we should be getting back. Now let's see a standard mechanism to check whether a relation is lossless. Let's take this example. Try to concentrate a bit more from here on. So consider this relation R. It consists of SSN, ename, pnumber, pname, plocation and hours. And suppose we are dividing this relation R or decomposing this relation R into these three relations. R1, which consists of SSN, ename, and the relation name is specified like EMP or something. So R1 consists of SSN, ename, R2 consists of pnumber, pname, plocation, R3 consists of SSN, pnumber and hours. And the dependencies that originally existed in R are SSN gives ename, pnumber gives pname, plocation, SSN, pnumber together leads to hours. So these are the three functional dependencies that exist in the original relation R. So let's see what is the standard mechanism to check whether a relation is lossless. For that, we need to construct a matrix. Now, try to understand how the matrix is constructed. The columns of the matrix are actually the attributes of the original relation. So the original relation attributes are SSN, ename, pnumber, pname, plocation and hours. So the columns of the matrix would be the attributes of the original relation. The rows would be corresponding to the decomposed relation. So this R is decomposed into R1, R2 and R3. So the rows would be corresponding to R1, R2 and R3. Now that is how we form the matrix. So this would be a 3 into 1, 2, 3, 4, 6, 3 into 6 matrix. Next, we need to understand how this A, B and all came. So let's go into that. Concentrate on this. So R1 consists of SSN and ename. Right. R1 consists of SSN and ename. So corresponding to SSN and ename, we put the alphabet A, and SSN and ename is there in the decomposition R1. Listen carefully to this. R1 consists of SSN and ename. So corresponding in R1 row, corresponding to SSN and ename, we put A. Now why A1 and A2 means if it is in the first column, it is A1. If the A is in the second column, it is A2. So R1 just consists of SSN and ename. So the rest of the columns would be written with B's, small letter B. So this is the first row, third column. That is why it is represented as B13. This is the first row, fourth column, 14. First row, fifth column, 116 for first row and sixth column. So R1 consists of just SSN and ename. So that's why A1 and A2 over there, rest are filled with B's. Now similarly try to understand for R2. R2 consists of P number, P name and P location. So we will be having A's corresponding to these three. So in P number we have A3. Why A3? Because A is coming in the third column. P name A4 and P location A5. Corresponding to the rest we put B, and when B is put, it is like this is in the second row. So B and first column B21, B22, B26. Hope you got how this B and A's are put. So for works on, it consists of R3 consists of SSN, P number and hours. So corresponding to these three, A should come. So SSN, since it is first column A1, P number third column A3, hours sixth column A6. The rest of the columns should be filled with B corresponding to the matrix location. This is B, third row, second column B32, B34, B35. So hope you got how we construct this initial matrix. So this is the first step. So corresponding to the attributes, we constructed the columns. Corresponding to the decomposed relation, we constructed the rows, and hope you got how we put A and B. So A's are put corresponding to the attributes in the decomposed relations in each row. Now next we are going construct the functional dependencies. Now we are doing all this procedure to conclude whether this is going to be a lossless join or non-lossless join. This is the standard procedure to do that. Let's see how we can conclude that. So let's take the first functional dependency that is given. SSN gives ename. So SSN gives ename. Now the thing we need to consider here is, first we need to look, SSN is the left hand side, ename is the right hand side. So in the left hand side column, that is SSN gives ename, in the SSN column, does it consist of at least, it is at least 2 A's. So there is 1 A over here, 1 A over here. In this column there are 2 A's. So it should consist, if we should check whether it consists of at least 2 A's. And ename column we should check whether it consists of at least 1 A. It consists of 1 A over here. If so, what we need to do is, wherever there is an A in SSN, corresponding to that row position in ename, corresponding to that B we can make it an A. We will see why we are doing so. So in SSN there were 2 A's. We can do 2 A's, and first we need to check whether this left hand side of this relation, that is SSN, consists of 2 A's, and ename, that is the right hand side, consists of at least 1 A. If so, the next step is, corresponding to all the A's in SSN, that is the left hand side, we can put A in the right hand side if it is not already an A. Over here it is already an A, so we need not do anything. Over here it is not an A, So as you can see, we cut this B32 and we put A over there. Since the A is coming in the second column, we denoted it as A2. So this can be done only if the left hand side consists of two A's and at least two A's. So if this was one A only over here, that is, this was not an A, just imagine this was not an A, we could not do this procedure, that is putting an A over here. So first we need to check whether the left hand side of the functional dependency consists of at least two A's in the column and the right hand side of the functional dependency consists of at least one A in the column. If so, we can do this. Corresponding to this A, we made this also A, and since it is coming in the second column, we denoted it as A2. Now let's see for the next dependency, that is P number gives P name P location. So what we need to do, we need to check whether P number, the column corresponding to P number consists of at least two A's. So P number, yes, it consists of two A's, A3 over here, and we need to, this is combined, P name P location is combined, P name P location is combined. So this it combined P name and P location should contain at least one A. So this does not contain. Now this contains A. Now both P name and P location should contain A because there are two terms P name and P location coming over here. So this contains A. There is an A over here. There is an A over here. So P number column consists of at least two A's. P name P location consists of at least one A. So what can we do? Corresponding to this A in P number, we can make A over here. So we cut this, make A. We cut this, make A. So that is how A4 came over here. This is since it is the fourth column, and A5 came over here. Now at this stage, at any stage in this procedure, if any of the row, in this R3, if any of the row consists of all A's, if any of the row is made to contain all A's at any stage, we can say this decomposition is going to be lossless. It's like playing bingo game or something. Like if a row as a whole consists of A's, it is like we can conclude that the decomposition is lossless. So in this, the decomposition is lossless since it consists of all A's. So just on taking the second functional dependency, we got one row as all A. Now imagine after this also we didn't get, we'll be going to the third dependency and taking that to consider whether we are getting any row with full A. We'll be looking one more problem from this. Hope that would be clear in a better manner. So you might be thinking, can you show me an example when the decomposition is not lossless? Now this was an example when the decomposition is lossless. What would be the case, or when can we conclude when the decomposition is non-lossless? So let's take an example for that. Consider this example. We had already seen this example for that functional dependency preservation example. So and we had seen that this is not a dependency preserving decomposition. Now let's see whether this is a lossless decomposition. So SSN ename these things, we are dividing it into R1, R2. R1 consists of ename P location and R2 consists of all this. Now how was the matrix constructed? You should be able to recollect that all the attributes consist of all the columns in the matrix. So SSN ename, P number, P name, P location, hours are the columns. We just have two rows because we have just two decomposed relations R1 and R2. So there will be just two rows, R1 and R2. Now how to place A and B initially? In R1, ename and P location are the attributes. So corresponding to R1, in ename and P location we put an A, and the number corresponds to the column. This is the second column, so A2, and this is the fifth column, so A5. Corresponding to R2, in all these columns, SSN, P number, hours, P name, P location, we put A. So SSN, P number, P name, P location, we put A. And how are the B's obtained? Wherever there is no A, we put B. So how to place a B? If B is coming over here, it is B11 because it is first row, first column. 13 over here because it is first row, third column. So that is how we construct this initial matrix. Now, as we saw for the previous problem, let's take dependencies one by one. Taking the first dependency, SSN gives ename. Take SSN column. It should contain at least two A's to make the right hand side cells as A. But unfortunately in this, SSN consists of just one A. So we need not check anything further. P number gives this. So for P number, it consists of only one A. So nothing needs to be checked further. SSN P number. Now note how to check this. SSN P number combined gives our. That's the third functional dependency. So SSN P number. These two. First column, third column. This combined, that is, we have an A over here, SSN and P number over here. So this can be considered. There is an A over here and over here. But there should be two rows like that. So we have just one row that consists of A's. So that we don't have two rows corresponding with A's. So this dependency can also not be considered for the process. So after going through the iteration and all the functional dependencies, we could not add any A's. So the original matrix is remaining as it is. So we did not get any row with full A. How do we get a row corresponding to full A? It is using that procedure which we followed in the previous problem. Like if we get two rows in LHS and one row in the RHS, corresponding positions corresponding to LHS in RHS is made A. Like in each iteration we keep on adding A's in each cell correspondingly. That is how an entire row can contain A. So unfortunately in this, no row contains A after considering all the functional dependencies. So we can conclude this is not a lossless join, or we say it is a non-lossless join. So the above decomposition is not lossless because there is no row with full A simple in the matrix. So that is the conclusion we can come to for this example. We can have one more example. Now this is a university question. This is how you will be getting a question for university. Let's have a look on it. Let's first try to understand the question. So assume that the relation R consists of P, Q, S, T, U. 5 attributes are there. So this is the relation. You are given the functional dependencies. P gives S, Q gives S gives T, TU gives S, SU gives P. So these are the dependencies that are given. And it is also given that the relation is decomposed into 5 relations. R1, R2. This should be R3 actually. They have missed the 3 over here. Consider it to be R3, R4, R5. So this is the decomposition. R1 consists of PT, this PQ, QU, STU, PU. This is the decomposition. Now they have asked to apply the standard algorithm to test if the decomposition is lossless decomposition. So we can see for the previous problem just consisted of 2 rows. It was pretty simple to arrive at a conclusion. So let's see if we get such a problem for exam, how to solve this and how to come to the conclusion whether this decomposition would be a lossless or non-lossless. So the first step is to construct this initial matrix. How to construct that? Consider how many attributes are there. This consists of 5 attributes P, Q, S, T, U. So that there will be P, Q, S, T, U, that many columns. How many the decomposed relation consists of how many relations? 5 relations. R1, R2, R3, R4, R5. So there will be 5 rows. R1, R2, R3, R4, R5. So this consists of the relations. This consists of the attributes. Hope the construction of the initial matrix is clear to you at this stage. So PQ, STU is the attributes. These are the decomposed relation. Now where to put A, where to put B? Now if possible, try to understand that on your own for a second and then continue. Otherwise I will just explain. So I'll tell a common mistake students can make at this stage. Now for putting A, some students unfortunately may consider P gives S. They may consider the functional dependency P gives S and put A corresponding to P and S. Actually, it's not the functional dependency that's to be considered to put A and B. It is the decomposed relation. Please keep this in mind. I have seen many students make this mistake. because both functional dependency and relations are given. They get confused using which or considering which should they put A and B. So it's the decomposed relation using which we should be putting the A's. So consider the first relation R1. P and T is there in R1. So we should put an A for P and T. Why A1 and A4? First column A4 because it is the fourth column. Rest of the columns we put B, and since this is the first row, second column 1, 2, 1, 3, 1, 5 and so on. Consider the second relation PQ. So corresponding to P and Q, P and Q, we put A for R2. Rest are B's. Third one, R3 consists of Q and U. So corresponding to Q, we put A, and corresponding to U, we put A. R4 consists of S, T and U. So S, A, T, A and U, we put A. Rest are B's. And corresponding to R5, we for P and U. P we put A, and for U we put A. And Y15, as I told, it is in the fifth column and first column. The rest are denoted by B's. Why it is a B53? It is the fifth row and third column. Sorry, this should be B52 actually. Sorry, this should be B52, this should be B53, B54. I have made a mistake over here, just ignore that. So this is the initial matrix. Just understand where to put A and where to put B, how to do that. Now, what would be the next step? We need to start taking the dependencies one by one and see the number of A's on left hand side, number of A's on right hand side and so on. If possible, try to pause the video if you have try to try this on your own. After considering some functional dependencies, or in one iteration, you should be getting one row with full A's. See if you're getting that by yourself. Otherwise, also it's fine. Let's continue and see how we can obtain that. It would be good if you can pause at this stage and see if you're getting that. So continuing with, so this is the initial matrix we have that we just constructed. So the first dependency we have is P gives S. We apply the dependencies in this order. We have P gives S, Q gives S. These are the dependencies given. So considering the first dependency, that is P gives S. So what we need to do? We need to see whether P has 2 A's. So P has 1, 2, 3 A's. So at least 2 is only required. P has 3 A's in this case. In S, there should be at least 1 A. Okay. Don't look this column. This column is actually the result after applying P gives S. Consider this initial matrix. So on applying P gives S, P consists of at least 3 A's and S consists of at least 1 A. There is a over here. So we can do the process. Now what was the process? Please listen to this once more. This is confusing, I know. P should consist of at least 2 A's. It consists of 3 A's. Here S should consist of at least 1 A. It consists of 1 A. So what can we do now? Wherever there is A in P, we can put or we can make that cell corresponding. So we can, this is the A1 for P. Correspondingly, this is the cell for S. So we can make this B13 as A. And since this is the third column, it would be A3. Corresponding to this A1, this can be made A. Corresponding to this A1, this can be made A. Okay. So that is how we obtained this table. So now this table, on applying P gives S, is converted to this table. Now you might be thinking, should we redraw this at each stage? Yes, for the exam, university exam, we have to redraw after applying each functional dependency because there is partial mark for each table. So after P gives S, after this functional dependency is considered, this is converted to A, this is converted to A, this is converted to A. Now another question that usually arises from student side is, now when we look for A's in considering P gives S, we look for A's. There are 3 A's in P, over here, over here, over here. And when we count for S, the A in S, should it come corresponding to this A's? It need not be. You just need to count the A's in that column and the A in the right hand column. It can be anywhere. So in this case, the A3 is not corresponding to any of the A's over here. It is just coming in the fourth row. Okay, so hope you got it. So there were more than 2 A's for P and more than 1 A for S. So we corresponding to P, wherever there was A1, that particular location in S is made to A. That is how we got A over here, A over here, A over here. And it is written as A3 because it is in the third column. So hope this stage is clear to you. That is how we keep on adding A's. Now, what is the next dependency we need to consider? It is Q gives S. Before going to the answer, let's try to apply that over here and see in the current table. It is Q gives S. So what we need to look for, does Q consist of at least 2A's? Yes, it consists of 2A's over here. Does Q gives S? So does S consist of at least 1A? Yes, it consists of more than 1A. So what can we do? This A correspond, wherever there is A in Q, the corresponding position in S can be made A. So this is already A due to the previous step. Now this can be made A. This B33 can be cut and made A. So that is done over here. So actually you need to redraw this table. You need to write that applying Q gives S, this particular conversion is made. You need to show that in your answer sheet. So we convert this to A. And after each conversion, we need to keep on checking whether any particular row is full of A's. If so, we can stop at that stage. Still now, no row consists of full A's. So we need to keep on continuing. Now the next dependency is S gives T. The next dependency is S gives T. So S gives T. So are there at least 2A's? Yes, all of them are A's. In T, at least one A do we have? Yes, we have an A over here and A over here. If so, what can we do? Wherever there is A in S, corresponding location in T, we can make A. So we can actually make this A, and this to be A. Because over here for S, it is A. And that is done, and we do it over here. So 3 more A's are added. So this is after applying S gives T. So this is the condition, and we need to check whether any row consists of full A's. Not yet, so we cannot stop. Applying the next functional dependency. Now it might be a bit more confusing because this dependency consists of 2 attributes in the left hand side. Let's see. Tu gives S, that is Tu, this 2 leads to S, this one. So when you check for A, please try to concentrate. You need to count, when you count for at least 2 A's, T and U both should contain A. So you cannot consider this in the count because only T consists of A and U does not consist of A. This cannot be considered because only T consists of A. This can be considered because T and U consist of A's. This can be considered because T and U consist of A's. This too can be considered. So there are more than 2 A's in TU. Now we need to check whether there is at least one A in S. Yes, there is more than one A in S. So if so, what can we do? Corresponding to this, and this row, not to according to this row we cannot consider because they are not A's. So only for both T and U. If both T and U consist of A's, that is this row, and this row, corresponding cells in S we can make A. So in this case it is already A. If not, just imagine if it was not A, we could make this 3 cells A. So since it is already A, after this Tu gives S, no change is made in the table. This table remains the same. But still for the exam, you need to redraw. After applying Tu gives S, you need to show that table. Okay. And still we have not reached any row corresponding to full of A's. Now I think this is the last dependency. Su gives P is the last dependency. Yes, Su gives P is the last dependency. Let's see whether this helps us in getting any row full of A's. Now Su. Now these are not even close attributes. S is over here, U is over here. So you need to be really careful when you deal with such attributes. S, U. So we need to see whether S, there is an A in S and U. So in the first row, it is there in S but not in U. Second row, there in S but not in U. There in S and in U. So one row we have got there in S, there in U. So second row also we got there in S, there in U. So we have got at least two rows where we have an A on the LHS, that is for SU. So there's this row, third row, fourth row and fifth row where we have an A for SU. Now taking P. For P, there is at least one A in the entire column. There are actually three A's, so there is at least one. So what can we do? Corresponding to this third, fourth and fifth. Why third, fourth and fifth? Because they are the ones that consist of A in S and U. So this and this. So corresponding to these three rows, we can make A in P. So we can cut this B31, make it A. Cut this B41, make it A. This is already A, so we need not do anything. So these two will also be converted to A's after applying SU gives P, and that is this step. So this is actually A1. This should also be A1. I have not shown that. So this should also be A1 after this step. I forgot to cut this. Please note this should be cut and written as A1. And now we have actually applied the last dependency. We need to check whether any of the row consists of full A's. Yes, the third row consists of full A's. A1, A2, A3, A4 and A5. It consists of full A's. Now what is the conclusion we can come to if an entire row consists of A? It is a lossless decomposition. This decomposition is lossless. Now after an entire iteration, now say SU gives P, also imagine we could not get an entire row with A. We may usually for any problem for the university we should be getting, usually they ask lossless, and unfortunately if you are not getting full A's, just try for one more iteration like this. Usually it should be lossless. So just go back and see if you have made any mistakes. Otherwise try for one more iteration like this and see if A's are getting added. That is, you need to go back and start from again from P gives S, and P gives S should be started from this table. Now in this case, if you are taking P gives S, there are at least two A's in this also. So you need to iterate one more time and see if a row consists of A's. If an entire iteration does not add any A, that's when you need to stop actually. An entire iteration means on applying all the 5 dependencies, not even a single A is getting added, you can stop. Usually that long problems won't be asked for university. In the first iteration itself, you should be getting your answer. So hope this is clear what lossless decomposition is. So in this video, it was a pretty long video, I know. We had discussed 3 terms: dependency preserving, lossless, and the first word was attribute preserving. So hope these 3 terms are clear to you. And the last lengthy problem which we discussed is a usual university question, this one. And one mistake students make is like they use this first table itself for each iteration and show using one table. That won't fetch you full marks. After applying each dependency, you should be showing the new table. That is how there is mark for each step. That is how if you are getting it, would be a 9-mark question. So hope this problem is clear to you. Thank you.